Today, we are going to look at how motors work in terms of the relationships between voltage, current, torque, speed, and mechanical and electrical power. Previously, you've done some calculations to figure out how much torque, rotational speed, and mechanical power your motor will need to move the cat up the hill. Today, we'll learn how we can use this information to spec a motor that will meet our needs. First, motor speed is linearly related to the voltage that you give the motor. For example, suppose I have a motor sitting on my desk and the motor shaft isn't attached to anything. When I connect the two terminals of the motor to a 6-volt battery, the motor will spin at some particular speed. If I now disconnect the battery and connect the motor instead to a 12-volt battery, the motor will spin twice as fast. Since I doubled the voltage, the speed will double also. We can relate the voltage to the motor speed using a constant called the motor velocity constant. And we can find the value of the motor velocity constant by dividing the speed by the voltage. If we plotted speed versus voltage on a plot, it would look something like this. And the slope of this line would be the motor velocity constant. Often, you can find the motor velocity constant quoted on a motor datasheet, given in units like RPM per volt. But if you don't find it quoted, you can usually calculate it from other numbers quoted on the datasheet. These other numbers are known as the no-load speed, or sometimes known as the free run speed, and the rated voltage. The rated voltage, or nominal voltage, is generally the highest voltage that the motor can safely take, and the no-load speed is how fast the motor spins when the shaft of the motor isn't connected to anything and is left to run freely, and the rated voltage is applied. Now, let me show you an example. Here, I've gone to the website of a company called Pololu, which sells DC motors of many different specifications, and the motors are well documented on the site. I'm going to go to the category of micro metal gear motors. Here, lots of motors are listed. None of them give the motor velocity constant, but they all give the rated voltage over here, and the no-load speed over here. So I can calculate the velocity constant by dividing the no-load speed by the rated voltage. Okay, so far we've only talked about voltage and speed, and so far we've left the shaft of the motor totally disconnected from anything. Now, let's suppose that we give the motor a constant voltage at its rated voltage, and we connect the motor shaft to something so that the motor has to exert some torque. Just to give an easy example, suppose I have attached a pulley to the shaft of the motor, and I've hung a weight from the pulley. So the motor has to exert a torque to lift up the mass, and we could figure out how much torque the motor would have to exert by multiplying the mass times the acceleration of gravity times the radius of this pulley. Whereas the motor speed is related to voltage, the motor torque is related to current. Now, I need to give a little aside here to make sure you understand something different about how voltage and current work. Voltage is pushed from a battery or power supply into the motor, but current is pulled by the motor out of the battery or power supply. For example, suppose I have a motor with rated voltage of 6 volts, and I hook up the motor to a battery or power supply that provides 12 volts. I will probably break the motor because the power supply will try to push all 12 volts into the motor, and that's more voltage than the motor can take. But suppose I have a motor that needs 1 amp of current, and I hook up the motor to a power supply that provides 5 amps. The motor won't break. The motor will be fine because the motor will only pull the 1 amp it needs and will leave the other 4 amps behind. So, back to our motor trying to lift the weight on the pulley. The heavier the weight is, the more current the motor will try to pull out of the power supply because torque is linearly related to current. For example, suppose I placed a 1 kilogram mass here and let the motor pull it up. The motor will pull a certain amount of amps of current from the power supply. If I now place a 2 kilogram mass here, twice as much torque will be required to lift the mass. So the motor will now try to pull twice as much current because current and torque are linearly related. Now, note that even when I attach no mass at all here, the motor still has to pull some current in order to spin. That's because there is some internal friction in the motor that needs to be constantly overcome with a little bit of torque in order to keep the motor spinning at a constant velocity. This amount of current that is needed to keep the motor spinning, even when there's nothing at all attached to the shaft, is called the free running current. Now, as I increase this mass, the motor will not only pull more current to account for the increased torque, but the motor will also spin slower and slower as more torque is required. Suppose I keep increasing this mass until the motor can no longer lift the mass at all, but also the mass isn't falling. The motor is holding the mass up. This amount of torque is what we call the stall torque. It's called this because it's the most amount of torque the motor can provide before it stalls or stops. The amount of current that the motor pulls when it is stalled like this is called the stall current. Now, just like we can find a motor velocity constant that relates voltage and speed of the motor, we can also find a motor torque constant that relates torque and current. We find this constant by finding the difference between the stall current and the free running current and divide the stall torque by this current range. Okay, now let's look at the next important thing related to motors. Remember how I said that as we increase the mass that the motor is lifting, the motor will slow down? We could make a plot that relates how much torque the motor is exerting and how fast the motor is spinning using something called a torque speed curve. In a torque speed curve, I make the x-axis be the speed of the motor in units like RPM, and I make the y-axis be the torque that the motor is exerting. The units of torque will be something like Newton meters in SI units or ounce inches in English units. Now, when the motor speed is 0, the motor is stalled. So that's when it's exerting the maximum amount of torque. I'll put a dot here and label this the stall torque. On the other hand, when the motor isn't exerting any torque at all, it is spinning as fast as it possibly can. So I'll put a point here and label it the free run speed or the no load speed. In between these points, the torque speed curve is linear, so I can just connect these points with a line. Now, note that this line is the relationship between torque and speed specifically when we are applying the rated voltage to the motor. If we decide to run the motor at a different voltage, less than the rated voltage, the no-load speed will be different. But we know how to calculate the no-load speed from the voltage already by using the motor velocity constant. So we could plot this torque speed curve for any voltage just by adjusting this no-load speed. Now, one thing we haven't talked about yet is the motor power. The motor converts electrical power, which we put into the motor, into mechanical power, which is the output of the motor at the shaft. We calculate electrical power by multiplying current times voltage, and we calculate mechanical power by multiplying torque times motor speed. Now, you might expect that electrical power and mechanical power will be the same, but that isn't really true because some energy is lost in the motor due to friction. The motor's efficiency can be calculated by dividing the mechanical power by the electrical power. The efficiency will always be less than 1 because the electrical power is the input and the mechanical power is the output. And the output will always be less than the input because some energy is lost inside the motor. In your assignment for this week, you will look at a specific motor on the Pololu site and use these equations and relationships that we know between torque, speed, current, voltage, and mechanical and electrical power to analyze and predict the performance of the motor. And you will do this in light of our power requirements from the last 2 assignments. Now, because we don't have any actual numbers from assignment 2, you can assume that the required mechanical power from each motor is 8 watts. Whenever possible, do your calculations in something like Excel or MATLAB or Python to allow you to do more accurate plots of torque, speed, and power, for example. You will turn in any hand calculations you do as well as your plots that you get from Excel or MATLAB or whatever you choose to do your plotting.